They're called neutrinos, and billions of them pass straight through our bodies every second. Neutrinos are some of the strangest and most mysterious objects in the universe. They're invisibly tiny and can travel through solid rock and even stars as easily as they do through space.
100 trillion of them, every second flowing through you, and I reckon they might do you some good, but no one knows it yet. Neutrinos, shooting all around me, oscillating soundly, impacting profoundly. Tiny ghosts called neutrinos, are they faster than light? They out of sight, but they might hold the universe upright.
If you put 100,000 of them on one side of a set of scales, they wouldn't even outweigh a single electron.
1930, Wolfgang Pauli told the scholarly neutrinos existed, but they thought he was twisted and resisted even listening. Your theory is far fickle, you're talking about star trickles. Neither you nor me will ever see these tiny particles. Pauli's undeterred, and the word flips him the bird. He got the math to back it up, even if it seems absurd. Then boom goes the atom bomb within the 1950s. Fred Rhinus, the new Bambino, going nuclear to find neutrinos. He finds them, grinds them, proves they exist. There must be zillions shooting out from the sun, and I miss. Ray Davis can't resist. He wants to look inside the sun. Counting all the neutrinos is how it will be done. It's a nuclear furnace, far enough to not burn us. He goes about finding neutrinos and earn us. Then he comes up short, just a third of what should be there. No fear, neutrinos vanishing in the thin air. The 60s, the 70s, the 80s go by. This guy keeps trying and dying. Is his equipment lying? No one's buying what he's selling. The numbers are telling, but there must be something wrong. But he won't change his song. By now there's 3 kinds of neutrinos we find: electron, muon, and tau. All flying blind like ghosts we can't see. We need a plan B. Another experiment, this time in Japan, but man, the results are the same lame game. When they count neutrinos, there's less than they claim there should be. You kidding me? When we go down in history, zillions of dollars, and we still can't solve this mystery. Now some people are saying the neutrinos are playing with our eyes, no lie. The solution is nah. 3 kinds of neutrinos, they're really the same particle. Imagine an article of clothing that keeps changing its state. Started at one thing, but wait, when we collate, it's too late. We oscillate into another form you'll never relate. That's why they seem fewer. You got the wrong viewer. We can detect and savor all 3 kinds of flavors.
In fact, there's probably more neutrinos in the universe than any other particle that we know. And yet, paradoxically, we know less about them than anything else almost.
Masatoshi Kashiba is the new kid in town in the Japanese mountains, where it's going down with Super Kamiokande, a chamber so grande you can basically see the path of neutrinos from point A to B. He proves what they stated: neutrinos are oscillating. One more scenario, this time in Ontario, inside of mine, to count the neutrinos, all 3 kinds this time. In 2001, the results come on strong, the numbers belong, the skeptics were wrong, that crazy Ray Davis was right all along. There still might be particles we'll never see, but definitely they're more than debris. An atomic trinity, shooting all around me, oscillating soundly, impacting profoundly. Tiny ghosts called neutrinos, are they faster than light? They out of sight, but they might hold the universe upright.
John Robinson, everybody. Right? Product of the South Bronx. That was probably the first time we've ever seen neutrino-based hip-hop, and you were here for the moment of creation. John Robinson, great job. Can't believe he synced it up to that. Happy Friday night, everybody. I am Bill Weir. I am so thrilled to be back. This is my 4th World Science Festival, and I love starting the summer by expanding my mind with the likes of all of you, and we're going to have a great time here tonight talking about the tiniest of particles out there. As Steve Martin used to say, we're going to get small tonight, because right now there are billions upon billions of neutrinos coursing through your body. They traveled all the way from the furnaces of the sun. Can you feel them? No, of course not. They don't interact with atoms. They're really tiny, but they made big news this last fall when we wondered if these outlaws were breaking the speed limit of the universe. Do they travel faster than the speed of light? Well, there's so much we know that we didn't know. There's so much to learn about it, and luckily we have a fantastic panel to fill us in. So let's have fun tonight and talk about these fascinating particles and bring out our panelists. Our first guest, she actually helps make neutrinos in laboratories. Her groundbreaking work has hinted that there are maybe more of these things than we can even imagine. She was inspired by looking through a friend's telescope back as a child, and Janet Conrad is with us today. Good to see you, Janet. Our next guest has spent over 20 years working on telescopes, not to detect light, but neutrinos. His quest has taken him even to the South Pole, where he's one of the world's leading neutrino experimenters there, buried deep in the Antarctic ice cap. We'll explain that coming up. From my home state, a Badger, University of Wisconsin, Francis Halzen. Doctor, good to see you. And finally, joining the stage, a colorful character. You may have seen him already at the Science Festival. Neutrinos, his favorite particle. He's interested in pointing out. Latest book, A Universe from Nothing, has been described as a brilliant guide through today's cosmological revolution. Theorist, director of Arizona State's Origins Project, Lawrence Krauss. Great to have all of you here. Welcome.
Good to be here.
And so let's talk about these little guys. Why should we care? Let's set our thesis for the evening's discussion. They don't care about us or our laws of physics. So, Lawrence, why do you love these little guys?
Well, they are the most mysterious particles in nature. They certainly don't care about us, but the universe doesn't care about us, and we still care about the universe. They defy common sense by going through us, as you pointed out. Every second of every day, there are tens of billions of particles going through every square centimeter of your body. During the day, they're coming from above, from the sun, but at night, when you're in your house and you're sleeping, remember this, they're coming up through the earth, through your house, through your bed. Think of that tonight when you're trying to sleep. So they're intimately familiar with us, and they probably hold the key to the mysteries that are going to direct us to really understand the fundamental forces of nature. Probably if there's one particle that is going to direct us towards new physics, we think it'd be the neutrinos. That's why we care.
And Janet, you said you decided in school, I'm going to make the neutrino famous.
Oh, yeah. In fact,
Why?
I think my neutrinos care about me.
You think so?
Yeah, I do. In fact, because there's a billion neutrinos in every cubic meter of space. There's more when you're closer to a star like our sun. But if you go the farthest out in space, there will be a billion neutrinos in every cubic meter of space. So if neutrinos are your friends, then you're never lonely.
And what first sparked your fascination in this particular part of particle physics?
Oh, neutrinos really have great personalities, actually. They are very, very independent particles, and that's what really Lawrence was saying. And so as a result, they have a tendency to not interact very often. But because they're very quiet particles, if in fact they were talking to other forces and other particles that we don't know about, you would be able to hear it with them because they're quiet. If you go to some places very loud, it's very hard to hear a very quiet signal. But since neutrinos are very quiet particles themselves, it's a good place to look for new physics, which is exactly what Lawrence was saying.
Right. Francis, why go literally to the ends of the earth in pursuit of these?
Well, this is a total act of desperation.
Come on, you just wanted to go to the South Pole.
Well, it's a dream since the 50s, when the neutrino was discovered. The neutrino is a neutral particle. It carries no charge. And so, because it carries no charge, it's the only particle besides the photon we can do astronomy with. Because if a particle has charge, we are surrounded by magnetic fields, so they swirl around and they forget where they come from. So it has been a dream since the 50s to do astronomy with neutrinos. Unfortunately, in the 60s and 70s, people figured out that it took a huge detector, size of a mile. And so since then, we have been thinking about how to do this. And so we finally succeeded in doing it.
Right.
That's the story.
Well, let's get the full story. John hinted at it a little bit in his rap, the origins of this discovery. Janet, help us understand how neutrino first came into our lexicon.
Well, what happened originally was that we were seeing that nuclei decay, and there was a problem with the decay of nuclei in that they were seeing particles come out from it. I think that they'll...
You want to go right to that? Yeah, so let's just set the stage historically, 1930s or so.
Mm-hmm. So in the 1930s, there was a real crisis actually in physics because people had discovered that nuclei would decay, and they do it dramatically in the sound, you'll see. And when nuclei decay, they found that two particles were coming out. There was the remainder of the nucleus and also something called an electron coming out. But you'll notice that those two were not back to back. Maybe they could play that again very quickly. Those two particles were not directly back to back. It was like something was missing if you wanted to fill in the whole of the circle of the clock. Or another way to say it, if you added up the energy of the two particles which are coming out, it should add up to the original mass of the nucleus, because E equals mc squared. It's everyone's favorite equation. But they were finding that that wasn't true in this particular case. And so I don't know if, I'm sure your mother always told you that energy is conserved.
Right.
Mine did.
Right.
And this is a case where that wasn't actually happening. So that was a huge crisis because this is a basis of our field. And so what happened was that Wolfgang Pauli actually decided to suggest that there was an extra particle in this picture. You just couldn't see it coming out for some reason. And so if they show the next.
And this animation represents exactly what you're talking about. This
so now watch this, right? So you've seen the two particles coming out. Watch for a third, a ghost particle that appears.
And this is exactly how this whole thing sounds, right?
Right. Yeah, you know, I sit there with my sources, and it's very loud in my lab.
Right, very sensitive.
Did you see the ghost?
There it is. It's there
Everybody
again.
saw it?
Yeah, it's coming
Okay,
out.
good. So, you know, at the time when Pauli actually suggested that this happen, the idea of inventing new particles was not something that was done. Today, you know, it seems to be the solution to all problems. They just invented a particle. But it was absolutely not something that was done. And so I think he was a little embarrassed by this. And so when he brought out this idea, he actually chose not to go and present it to his colleagues. He wrote a letter instead, which starts out, "Dear radioactive ladies and gentlemen." And instead he went to a ball with his new girlfriend.
Is that right?
Yeah, no, that's absolutely right. It says that at the end of the letter. I'm sorry, I can't actually be at your conference. I have to go to a ball.
Man's got his priorities.
Yeah.
But Lawrence, talk about, as she mentioned there, in the 1930s, how was this received? How radical was this for
Well,
those
you know,
times?
as you point out, nowadays we're used to a plethora of new particles, but at that time there weren't many in nature. And in fact, the neutron had just been discovered, and the idea of such a proposal was outlandish, and more importantly, here was a particle which was designed to not be seen. Nowadays, theorists like to do that. You know, they don't worry about inventing things like, say, string theory that we can't see. But then, you know, the idea that you had a new particle, but in some sense, and Pauli was one of the first to say you'd never really see it. It would have to be, if it didn't have any charge and it didn't interact, it basically would be invisible. And I think the community was quite skeptical. And in retrospect, it's kind of obvious that you needed it, but it took a long time before any experimentalists had the gumption to look for it. And in fact, it wasn't Pauli, but his Italian colleague Enrico Fermi, I believe, who called it little neutron, which is neutrino. So neutrino is little neutron in nature. The neutron had been discovered. It was a neutral particle. And the neutrino, because it didn't take up much energy or much mass, it was just a little bit of difference there. It had to be very light, so light, much lighter than any particle in nature that was known, and have an interaction strength that was much smaller, so little neutron.
And how specific, Francis, was he in those early days? How much of his theory has held up
Well, I'll answer your question, but let me first make a comment about the actual experiments. Because Pauli was a theorist, but he was well aware of what was going on. And if you actually look at the work, there was a man named Charles Ellis at Cambridge who did these experiments where he looked at radioactive decays of nuclei. It's exactly what he looked at was exactly what Janet was explaining. If you have a nucleus decaying and you see two particles going that way, you know that there's something going that way, because you have to conserve energy. It's billiard ball physics. And in fact, he studied this in detail, and he saw this particle he saw this missing energy that had practically no mass. So for all practical purposes, he actually discovered a neutrino. So it's a bit unfair. I made the same mistake.
In fact, that's the way we discover particles nowadays often, is by not seeing them.
Yes, by not seeing them.
Because
exactly.
if you can do an experiment carefully enough, and you know you can prove there's missing energy and missing momentum, that's how we identify many particles.
Actually, by today's standards, he would have discovered a neutrino.
Standards have changed, whether they've gotten worse or better.
You know, that was not seeing something was not evidence. Now it is. Well, there is a side, an important aspect of this. Many people, many scientists, including Niels Bohr, believed actually that there was no neutrino, no particle, that simply energy conservation was wrong. But we know much better now. That was a very ill-advised, a poor decision on his part.
We have a different view. I like to point that out. People think, we teach physics the wrong way in school so many ways, but people say, energy is conserved, and that's something we decided. It's like a law, and we write it down, and we just decided it had to be there because we all shook hands. But in fact, we now understand that these things are related to symmetries of nature. And if the laws of physics don't change over time, that implies energy must be conserved. So now we would be much more loath to give up that idea, because we understand that that's a fundamental symmetry of nature. The laws of physics don't change over time. We can detect that. And that requires energy to be conserved. So no one would blindly, at any scale, even the quantum mechanical scale, suggest it would be thrown out now.
But I didn't answer your question. I think that up to the point where Reines discovered the particle by putting a detector close to an enormous source of neutrinos, which is a reactor, up to that point, I think many people thought that this was like a mathematical trick to make the theory work, and that was actually not a real particle. And so it was quite a shock. I was lucky enough to have met Reines before he died, and it was clear that it was quite a shock to them to prove that this was a particle like any other particle, just harder to detect, and not some mathematical concept. In fact, I refer to doing astronomy with neutrinos. It's very funny because as soon as Reines' paper appeared, practically everybody had the idea that you could do astronomy with it. Before, nobody had the idea. And just the fact knowing it was real, but it also tells you what the attitude was before.
Right.
Probably was mathematics.
If you're a theorist, as an experimentalist, you don't take things seriously till they're seen. It's really amazing to me in my career. Lots of papers that I've written, I could have been written before, but you don't take them seriously till people observe it. It's really kind of an interesting sociological phenomenon.
What is, from an experimentalist point of view, how does that work?
I think what they're saying is absolutely true. In a really healthy situation, sometimes experiment chases theory, and sometimes theory chases experiment. And you want to have this cycle, and that's what's been so terrific about neutrino physics, is that the cycle is going around and around over a very short time scale. That, the theorists come up with something, we start exploring it, we discover maybe what they say, but also something new about it. Oscillations are a good example, and then you turn back around again on this wheel.
Right.
And that's just the best situation to be in if you're a scientist, right? There isn't really a very big separation between what theorists do and what experimentalists do.
Usually. In the best of
You're not the Jets and the Sharks of science.
Yeah.
All right, well, let's talk about from discovery today. And Francis, you talked about setting up that detector near the reactor. So But was that it? Did they suspect they came from somewhere else as well?
No, Reines was one of the main architects of the atomic bomb. And after the war, he had set as his primary goal to discover the neutrino, to prove that this particle really existed. And so his first idea was very interesting. He was actually going, in the 40s and 50s, there were exploding bombs left and right, and bombs produce neutrinos. And so he was looking for a healthy source of neutrinos, and the atomic bomb was it. So he had the idea to build a detector, but of course the detector you had to put it close to the bomb so it would explode. The way you solve that is you build a deep hole, and so as the bomb explodes, your detector starts falling in the hole. And so the time it falls, you have the time to do your experiment. and it's while he was thinking about
Is there a graduate student holding that?
I don't know where the graduate students are.
2 of them. One for redundancy.
But it's while he was thinking about this crazy idea, which may have worked actually, is that he had the idea maybe it's better to put it close to a nuclear reactor. Because I suppose it's clear that as these particles don't like to interact, a way to overcome that is either to have a very big detector, which we do nowadays, or to have a very healthy source of neutrinos. And so a reactor is it.
And it's interesting that relationship between experiment and theory again, because when Fred did that experiment, the theory was wrong and predicted an interaction rate, which is actually different. And his experiment actually agreed with the theory at the time, and it was wrong by a factor of 2. And ultimately, which is amazing given how hard it is. Even to get within a factor of 2 is an amazing result.
Yeah.
And but I think that's one of the reasons it took 40 some odd years before he won the Nobel Prize for that discovery. But he did tell me, by the way, he sent a telegram to Pauli the day they discovered it too, to let him know it was there.
But at what point did they start to consider the sun, the stars, the natural world as a source?
So the first experiment that was a solar neutrino experiment was actually started in the early 1960s. And so let me just begin by explaining why neutrinos actually come from the sun. Maybe I should start there.
Okay.
And this is why you should care about neutrinos, okay? Because the very first interaction that happens in the sun actually is a process which involves the neutrino. So what happens when you have that first fusion that occurs, a neutrino, it comes out of that fusion process and it starts the entire cycle in the sun. So when you are really happy to wake up and find that the days are much brighter and longer, you can thank neutrinos for those. And so you can actually take a detector and image the sun in neutrinos. And so that's actually been done by the Super K experiment, which was one of the experiments shown in the RAP. But the attempts to do this started actually in the early 1960s, and I know this sounds strange, but to see the neutrinos from the sun, you actually have to go very, very far below ground, about 4,000 feet below ground. So you're very far away from all of the noise that comes from the rest of the particles that are inundating us in this world. And so a detector was built by Ray Davis, who was one of the people who was also in the RAP. And he went out to measure the number of neutrinos that were expected from the sun. And there was a prediction from a man named John Bacall. And so Davis went out and did his measurement, and they did a comparison to prediction. They saw neutrinos from the sun, just not enough of them.
Right.
Actually, the interesting thing is, it's amazing that Ray Davis did that experiment. There have actually been other ones earlier, because really the rates were really uncertain, and there was an experiment deep in a mine in South Africa, in fact, that Reines tried to do to look for it. But to think, Ray Davis was a chemist, not a physicist. And to think that and this experiment depended on chemistry. Of the billions and billions of neutrinos that go through there every second, it was 100,000 gallons of cleaning fluid. Right. One will turn the nucleus of an atom of chlorine into the nucleus of an atom of argon. So all you have to do is detect a single atom of argon and 100,000 gallons of cleaning fluid. And
That's
who
all.
would think you could, in science fiction, they'd never propose that. The fact that Ray Davis would had the guts to do that with a very, at the time, tenuous, I think it was the way you described the theoretical prediction, is an amazing fact. And I just hold him in such high regard that he was able to consider doing that.
But
Yeah.
I should just say, and this just starts to illustrate what happens when we're trying to look for these neutrinos. We need enormous detectors in order to look for neutrinos, because even if you have a great deal of rate of neutrinos coming through, they don't interact very often. So if you want to give them enough material to interact in, you have to build something which is very, very large as their targets. And so that's why he needed so much dry cleaning fluid.
And he didn't even know if it would be enough, because at the
Right.
time, the predictions varied by a factor of 10 each time. And I remember years later, I was talking about neutrinos from the Earth in a paper I did, and I talked to geologists. And this was years and years later, and I said, you should be looking for these things from the Earth. And they said, when I went to school, people didn't believe in neutrinos. You want you to do, and he did his stuff 30 years earlier. It's amazing. It was incredibly prescient.
What I find stunning about solar neutrino stories, you mentioned that Reines was off by a factor 2, but if you discover neutrinos, who cares about a factor of 2?
Eventually.
Here, I actually had a conversation with John Bacall once, because this factor, it was another factor of 2. Davis did this difficult experiment. He found half the atoms he was looking for every month. He went through his cleaning fluid every month and looked for the atoms that had been converted by solar neutrinos. And so I told John Bacall, if you said you were right within a factor of 2 and declared victory, you'll get a Nobel Prize. And he looked at me, and actually John Bacall, for 30 years, he got, just quite insulting, I think, what I said. But he got continuously attacked, by bright young people who had the idea why his calculation was wrong. And he stuck to his gun all the time. I actually saw him be insulted at conference for being naive.
Wow.
It was painful to watch sometime. And when the snow experiment in Canada finally confirmed that neutrinos were oscillating and that his astrophysical calculations were right all along, it was an incredible success.
Indication.
He told me, if I feel like I've been in jail for 30 years, I finally got out.
Wow. The loneliness of theory. So there was the sun standard model, and then the standard model. I guess we should help everybody help me understand, what is the standard model?
Well, we call the standard model. It's probably one of the greatest triumphs of the human mind, in my opinion. It can fit on a T-shirt, and it describes everything we can see. It tells us that everything we see in nature is made up of a few fundamental particles. In fact, everything we can see is essentially made up of just the first family. But there are 3 different kinds of quarks at the top there. It's actually 6 total. We call them up, charm, top, down, strange, bottom. But in each family, there are 2 quarks and a particle called a lepton, an electron. Those are the fundamental particles that make up everything we see. And in fact, there are just 3 forces of nature that basically govern everything that happens on a human scale. And that entire edifice was built up theoretically over a period of about 40 years. But one of the key predictions of that standard model is, as you notice, there's a row missing, is in order to fit the picture together with the forces of nature and the observed radioactive decays, there had to be one type of neutrino for each type of lepton. And I hope we'll see suddenly the standard model appear before us. And
yes.
There we go. And it is amazing that in fact, a number of these particles were predicted before they were seen. In the case of neutrinos, actually, they were seen before they were predicted. But once we saw 2 families of neutrinos, then in order to fit everything together, we needed a 3rd family based on experiments. And that simple picture comprises basically the entire visible universe and almost all the processes that are relevant to our lives. and these three known forces. And there are incomplete aspects of that standard model. So all of the predictions have fit together. There's one part that really hasn't been measured yet, and that's what the Large Hadron Collider is being built for. There's a part of it related to something called the Higgs particle, and there's tentative evidence that it's been seen in the Large Hadron Collider. It may be confirmed, and if that's the case, it really is kind of amazing. It's one of the few instances where theory has really led. Most often, no matter what Janet says, most often physics is led by experiment. As a theorist, I'm happy to say that. Experiments surprise us and direct our thinking. But this is a case where this picture was built up over 30 years, and it would be amazing to me if it's right. Because that's the other thing most people don't realize is most theories are wrong. I mean, if they weren't, anyone could do it. And so I would be amazed if it all works out to be right. And neutrinos are an integral part of it. It just doesn't work mathematically unless you add them into the theory. And that's why we know there are three of them. But the interesting thing about the standard model is it's incomplete. And it's neutrinos that have told us it's incomplete. Because in the standard model, it turns out neutrinos are massless. Of all the particles there, except of particles of matter, neutrinos don't have a mass. And of course, the observation that neutrinos oscillate is only possible if neutrinos have a mass. And that tells us, we know for certain, there must be new physics beyond the standard model. We don't know what it is, but neutrinos are pointing in the right direction.
Well, let's get into oscillation, and you have a good experiment on this, but help us understand that. There are three flavors.
Right. So
vanilla, pistachio, no, electron, muon, and tau, right?
Or tall grande and
Venti.
Right. To understand neutrino oscillations, you really have to buy into the idea in quantum mechanics that particles behave like waves. And so let me give you an example of something that waves do that is absolutely unique. Particles can't do this, okay? So what I have here is I have two tuning forks. And I have slightly mistuned one tuning fork compared to the other. I've added a little bit of mass right here to mistune my tuning forks. And let me show you a trick that only waves can do, okay? Did you hear a wah, wah, wah?
Yeah.
Was that clear to everybody?
Do it again.
Okay. Thank you.
Please.
Wah, wah, wah. It's coming and going, coming and going. In fact, if it really went fast, you would call it a shimmer. And waves can do that because the two tuning forks, the waves of the two tuning forks are interfering. This idea that they're coming and going is the same as what happens with our particles, the neutrinos. We start out with neutrinos, which are, for example, the electron kind of neutrino, or vanilla if you prefer. And that seems to disappear and then come back again, and disappear and come back again in our detectors. And so what's really happening is it's turning into another flavor, but our detector can't taste that flavor. So to our detector, it seems to just disappear. And so Lawrence said that what this means is that neutrinos have to have mass. So you should immediately ask me, why? Okay?
Why?
Why? And, so let's think of this as like a clock. As the wave goes by up and down, wah, 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 it's counting like a clock, right? And now let's think about what it means for there to be a passage of time. It turns out that if you could go the speed of light, time would be frozen for you. The clock would never tick, okay? The reason for that is because, as you're going the speed of light, the light is trying to catch up with you that's coming from the face of the clock, and it just always looks frozen to you. This was one of the ideas that Einstein put forward. Well, what the neutrino has inside of it is a clock. It's changing its flavor. It's coming and going, tick, 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 tick. For it to be able to do that, then, what it means is that it can't be going the speed of light. And it turns out that what makes the difference between a particle that can go the speed of light, like a photon, and a particle that can't is mass. Mass is what's preventing you from being able to go the speed of light. And if my neutrino has a clock, if it can oscillate, then that means it has to have had mass. So that's the whole thinking behind all of this.
Francis, I mean, what does this mean for the bigger picture, the oscillation idea?
Well, I mean, the biggest impact of oscillations was what Lawrence already mentioned. If we had gone a little bit more into the standard model, we would have realized that anything you put in these 3 boxes is not allowed to have a mass. So it was the first hint, not a hint, it just was the first experiment, the observation of oscillations, that pointed that there was something wrong with the standard model. And that's the biggest impact of oscillations. I think what's also interesting is, and we're talking about neutrino physics here, so neutrinos now are considered like by particle physicists as maybe being the canary in the coal mine. The first hint we get that there is something wrong with this beautiful edifice we put up, even if it's hard to put it on a t-shirt.
It's hard, but you can do it.
But
I should have worn it.
Small text. And so, so a lot of neutrino physics is now driven in the study of these oscillations with the hope of seeing neutrinos doing other things than having just mass, and starting to tell us how to, what's wrong with the standard model and how to make the next step, because that's the next step for particle physics.
And being, the other thing I think is really important, and you just said it perfectly, we get really excited when we're wrong. And I think that's something people don't understand about science, is that being wrong is great. I love to do it. Because it means there's more to learn. And I think it's one of the things that really characterizes science, as opposed to, say, religion, that it really...
Way to slip that in.
Yeah, I had to slip that in. But but the idea of being wrong is, and you change your mind. And in fact, the way you become well known is by proving your colleagues wrong. And so, and I think that idea that you can throw out your ideas like yesterday's newspaper, once nature tells you it behaves differently, is one of the greatest aspects of science.
Right. That being said, is there a 4th flavor of neutrino, a 5th? I mean, what's next?
So if there's a 4th flavor of neutrino, it doesn't behave the way these neutrinos do. Okay, we have been able to do experiments which show that these are the set of 3 that behave in a very specific way. But yes, actually, I'm looking for a 4th kind of neutrino. That's one of the things I do for a living. It's called a sterile neutrino, which is really a sad name. I didn't name it. But it's a neutrino that doesn't interact the way the other neutrinos do. And there's a lot of good reasons to introduce it into the theory. But it does bring you back around to something that Lawrence said that I actually a little bit disagree with, because it doesn't fit that well on a t-shirt, and it's kind of embarrassing, okay? That is a lot of elementary particles. I mean, you would like your theory to be much more compact and cleaner, right?
That's what I was alluding to.
Yeah,
I don't know, compared to the number of elements and all the diversity of nature.
It looks like the elements, doesn't it? It starts to look like a periodic table.
It starts to.
And you were able, you said, and this is absolutely true, to know that there had to be that 3rd neutrino out there because there was a hole in that chart. And that was exactly the thing which made us believe in the periodic table, that they were actually able to predict elements because there were holes in the chart, and then they were able to go and find them. And so...
But there's no hole in that chart for your 4th flavor.
Oh, well, maybe there is. Now that neutrinos have mass, you're going to have to expand that somehow. And so it leads you to want to bring in another row. And in fact, then that makes you start to think, just like with the periodic table, does something lie beneath, right? With the periodic table, what we realized is that all of those elements were not fundamental at all, that there was something else there. And I think you look at that and you say, well, there's a lot.
In fact, it's interesting, because as a theorist, we're always trying to simplify it. We ultimately think the laws are simpler and simpler. Maybe they're not, but we hope they are. And in fact, the notion that neutrinos have masses, The masses are very, very small, and they're very small compared to the other particles in nature. It's hard to understand, but it turns out if you unify the three known non-gravitational forces in nature, the strong force, the weak force, and the electromagnetic force, in something called a grand unified theory, then there's an argument that was presented. If the forces are unified at some very small distance scale, then that could naturally translate, for reasons I won't go into here, but it could naturally translate into very small masses for the neutrino. So in fact, the fact that neutrinos may have mass is another signature that maybe this indeed does get simpler, that in fact there is a simple, single grand unified theory. And one of the exciting bits of neutrino physics is it may be the only way we can directly probe for this wonderful idea of grand unification.
Wow, that's amazing.
But so to come back to Earth, I think I should point out that nobody has any clue why there are three families, why there are, these three columns. And in fact, if only the first one existed, we would live a happy life.
Yeah, in fact, when the second column was discovered, Robbie said, who ordered that? Because they're all copies. They don't need, as far as we know, well, there may be deep theoretical reasons why you may need at least two, and now three, it turns out, because you need three to make matter instead of antimatter in the universe, it turns out, and recently a Nobel Prize was given for that. So the need for at least three families may be related to the fact the universe is made of matter instead of antimatter.
Yeah.
Well, let's pivot to neutrinos as sort of messengers from the universe. So this will take us into some of France's work down in the Antarctic. But we think about dark energy and cosmic rays and seconds after the Big Bang and what they can tell us about this. But Lawrence, to you, what was the most important moment in recent history?
And certainly in recent history, the most amazing moment was February 23rd, 1987. You all remember that. That was the day that we observed something that, again, I never would have thought we'd seen. When stars explode, the brightest fireworks in the universe is a supernova. It shines with the brightness of 10 billion stars. But it turns out that all of that light is just a small fraction of the energy that's produced in a supernova explosion. Most of the energy comes out in neutrinos. We predicted that, and all of nuclear physics told us that should be the case. And in fact, I even did calculations based on it, but I don't think any of us ever thought we'd see it. But in that day, in fact, and some of us have predicted how many you might see in a detector of the type that we're discussing here. You predict if a star exploded on the end of the galaxy, 10 or 20 neutrino events. February 23rd, supernova was seen, and then the neutrino experiments looked at their data and discovered 20 neutrinos, which were 19 neutrinos, which was essentially almost exactly the number that the simplest models predicted. And that, again, amazed me. The fact that, because these neutrinos are coming from the dense cores of an exploding star, where the densities are unimaginably great, and yet the laws of physics, as we thought we understood them, gave the right answer. But the other reason, and this leads to the other reason we should care about neutrinos, because it turns out, without neutrinos, the stars wouldn't really explode, as far as we can tell. It's the fact that the neutrinos, it's so dense that even neutrinos, which interact weakly, on their way out of the star, pump enough energy into those outer layers that they cause them to explode. And that's important for you and everyone in the audience, because we're only here because they exploded, because every atom in our body came from an exploding star.
Right.
The only atoms that were created in the Big Bang were hydrogen, helium, and a little bit of lithium. And for some people, lithium is important, but for most of us, carbon, nitrogen, oxygen, iron, all those things are only created in the cores of stars. The only way they could get in our bodies is if those stars were kind enough to explode, and they wouldn't have gotten in our bodies if it weren't for neutrinos.
But let's back up a little bit to that day in 1987. So there were sensors, if my reading was right, in the Balkans, in Ohio, and Japan, right?
Right.
Yeah.
And out of the trillions and trillions and trillions of neutrinos that came out of that supernova, 19
events, 10 in one and 9 in another. And it's amazing. That doesn't sound like a lot, but in the neutrino business, in a 10-second period, to get 19 events.
So that was in a 10-second period.
Right.
Okay.
And in fact,
that
actually,
was
there's another
what was so
interesting
important.
statistic.
Both saw them at the same time. The two detectors that saw a large number of neutrinos, they saw them really at the same time.
By
As
the
well
way,
as we could tell.
thousands of papers have been written on this 19
Those are the
event.
most
wrote
studied
a few
neutrinos
hundred of
ever.
them myself.
Yes.
Right.
But
That's
the-
the mother lode of neutrinos.
Absolutely.
19 of them.
There's an interesting statistic too, which is that if you actually work it out, if someone on Earth saw them, one of them, because if you work it out, all the people on Earth, someone who was blinking at that time, there would have been one neutrino that would have interacted in someone on Earth and caused a little bit of light in their eye. So if you work it out, the high probability is that someone was blinking, saw a bright light, but didn't know what it was all about.
Wow. I'm going to write a screenplay based on that idea. That's interesting. So this tells us it's fingerprints, I guess, of what's happening light years away.
It really was I think the really origin of really neutrino astronomy. The astronomy from the sun was one thing, but this was the evidence that neutrinos could tell us about things happening far away in environments that nothing else could reach us from except neutrinos.
But also, I mean, certainly, that's obviously true. But also, and we often forget that, these few neutrinos made stellar theory believable.
Yes.
I think stellar theory was a very academic subject. And I guess some people didn't even believe it was controversial. It's very difficult to think back now. But by seeing these 19 neutrinos, it was clear that stellar theory, where stars collapse to a neutron star, I mean, that became, everyday physics, suddenly, by seeing a handful of neutrinos.
You asked me why I went into neutrino physics. This actually happened just as I started graduate school.
Wow.
Yeah, it was really, really exciting. It happened, and then my professor came striding into the classroom to tell us all about it. It was great.
Also, if this happened, I mean, we are now, this took us by surprise. As far as I remember, it was an amateur in Australia who discovered 87A.
Was
and
a
then they
Canadian astronomer who
and-
looked at the photographs the night afterwards and saw it.
Yeah. And so then the physicist went to look to their data. Now, all the detectors on the Earth, there are quite a few of them that can see supernova, including ours at the South Pole. We are ready to see this. And so what we are trying to do is, if a supernova went off now, first of all, my cell phone would go off.
You have a neutrino app on
It's
it.
actually turned off.
And theirs can too.
And
you can sign up for this.
Yes.
It's called SNEWS, SNEWS. You should sign up for that, and your cell
And
phone
so
will go off too.
when the signal arrives, every experiment sends this signal to a computer in Brookhaven National Lab, not too far from here. And that computer sends out an alert to the whole astronomy community. And it would actually be the first time that astronomers could point their telescopes and see a supernova happen. Now they're always caught long after the explosion. The interesting stuff happens in the beginning. And so the neutrinos would tell the astronomy community, point your telescope, it's coming. You have about 3-4 hours. And, this would be the scientific event of the century. So we're all waiting.
Yeah, it's my friend Kate Schulberg who put this together. And she originally called it potatoes, which stands for point over there at that old exploding star. It spells potatoes. But then she decided snooze was a better name. So.
It would be remarkable. Unfortunately, fortunately, they don't explode too often. But
They're happening less often.
Yeah. Well, we're around, but they go about
close.
once per 100 years per galaxy. So it's not, and the neutrinos that we probably see are probably in our galaxy. And so the one we saw, by the way, 1987A, was not quite in our galaxy. The reason it was seen in Australia, it was in a nearby galaxy with the Magellanic Clouds, close enough to still produce a signal. So it's not the kind of thing we expect to happen every 6 months or every year, and that's why we have to be on the lookout. And that's why amazing these experiments, if they're offline for the wrong 10 seconds, then
that's the reason they are coupled up through a computer, because at any time someone could be calibrating their detector. You know, I cannot imagine what I would do if a supernova went off and someone was messing with something.
Yeah.
But
So-
you might ask then, if he says that you get 2 or 3 a century, why we haven't seen supernova lately. In fact, we haven't seen supernova in the sky for many hundreds
Yeah,
of years.
it turns out most of our the easiest place to see supernovae is in other galaxies, because most of our galaxy is invisible to us. It's obscured by dust. And so even though they've been happening, the last one that was seen in our galaxy was by Kepler about 400 years ago. And the only way we'd see them, a lot of them in our galaxy, is by the neutrinos. We actually wouldn't be able to see the light. The other thing, besides telling us about astronomy, that we should point out is that these neutrinos, while they're messengers of the universe, they tell us about particle physics. There were hundreds of papers, and I wrote a few of them immediately after these were seen, that told us limits on the neutrino mass, because if the neutrino mass was heavy enough, they'd be traveling slow enough that different neutrinos of different energy would spread out, and the signal would be much longer than 10 seconds. One of the most interesting things for me, because it surprised me, was something we realized, which is if it weren't for general relativity, neutrinos that were observed in 1987 would have been observed in 1986. Because time slows down in a gravitational field. And the neutrinos that come all the way from that Large Magellanic Cloud took 6 months longer to get to us because of the fact that space is curved. And in fact, the fact that they arrived within 3 hours of the light allowed us to put the best test of general relativity that had ever been done, because neutrinos and photons came and bent the same way in a gravitational field. It amazed me when we first realized that. It's because general relativity is responsible. A 6-month delay. It's amazing.
Francis, what about dark matter? What can they tell us about dark matter?
There was a time that neutrinos were the natural candidate for dark matter, because in fact in 87, that was already too late, but supernova 87A was then the best upper limit on what the mass of the neutrino was. It didn't come from accelerator experiment, it came from 87A. And so if you give neutrinos a tiny mass, they could be the dark matter. And this was perfect. You don't have to invent anything new. There you have already a particle, just give it a tiny mass, and the problem is solved. Unfortunately, this tiny mass is too large. It's ruled out now. Neutrinos still play a big role in shaping the universe and the way it looks, but they cannot be the dark matter.
But they set the prototype, in some sense, for the dark matter. I mean, the idea, the notion, it seems fantastical that there's dark matter, and it sounds too crazy to be true. But in fact, we know there are lots of invisible particles, and neutrinos are the perfect example, that were created in the Big Bang. The same nuclear reactions that produced the helium and the lithium produced those very neutrinos. We know they're in this room today. We have no way of, at this point, of experimentally detecting them, but there's something like 400 million in every cubic meter of space in this room left over from the Big Bang. And all you have to do is give them a little mass, as Francis said, and that gives us confidence that there could be other particles in nature that easily could have been produced in the Big Bang that wouldn't be observable. It's not so crazy to think of it.
Right.
But so this was the perfect theory, actually. Unfortunately, it was wrong.
That happens to perfect theories.
That
was a good while it lasted.
That was the perfect dark
Nature
matter
isn't very
theory.
perfect, really. You know? This is one of the things we like to believe, that nature is elegant. That would have been such an elegant solution, you know. And
but
nature,
the real solution will be more elegant. That's all.
Oh, really?
Once we get our minds around it.
We're just not there yet.
Yes.
But if we're inspiring future neutrino astronomers here, Jenna, how do you measure the information that is traveling all this way?
So, well, first of all, I need a really large detector, which is part of what I find is the attraction of going into neutrino physics. I like really big things, you know. And so I really like that aspect of it. You never actually see the neutrino itself. It is neutral, and it turns out that all of the detectors that we have react to electromagnetic charge. So if it doesn't carry that, then you actually can't see it. So you have to understand it from its collisions, its interactions within your very large detector. So for example, it might come in and interact with some dry cleaning fluid and turn it into some other element. And that was how Ray Davis's experiment worked. Or it might be that it comes in and it produces a little bit of a charged particle coming out. So for example, if an electron neutrino comes in and it interacts, it'll produce an electron, which carries electric charge, out. A muon neutrino produces a particle which is called the muon, which is really the big brother of the electron. The tau produces a tau particle. And we can see the electron, the muon, and the tau in our detectors. They have very distinct signatures. And it might be that we see them because they ionize material in our detector, which means that they travel along and they rip off the electrons as they travel along, and we can see that little trail of charge. You can also see this through a really neat effect, an effect which is called Cherenkov light. So
yeah, I think we
show this.
can show it.
This is something which is really a classic effect from reactors. So you're actually looking at a reactor core in this picture. And so Cherenkov light is an effect where a charged particle is going faster than the speed of light in a medium. Don't get excited here, okay?
Yeah.
So when people say nothing can go faster than the speed of light, and that includes neutrinos, okay?
They don't, yeah, they don't.
They don't. They're leaving a little bit out of the phrasing. Nothing can go faster than the speed of light in a vacuum. But it turns out that light, as it travels through matter, gets slowed down. That's an effect called refraction. So you might have seen a beam of light go into some material that's relatively transparent, and it bends. If you put a pencil into a glass of water, it'll look like the pencil is bent. That effect means that it's possible for a particle to actually be traveling faster than the speed of light in the material. Now, when a plane goes faster than the speed of sound, you get a boom, right? You get a sonic boom. And when a particle goes faster than the speed of light in the medium, you get a photonic boom. You get a boom of light coming out. And that light that's coming out is this beautiful blue color when you look at it. In the visible, what you can actually see is this absolutely gorgeous color called Cherenkov light. And the Cherenkov light you can then detect. And you detect it with a kind of detector which is called a phototube, which actually works on a principle that Einstein figured out. It's what he won the Nobel Prize for.
Interesting. Francis, tell us a little bit about your detection
Yeah, in
experiments.
fact, this was the perfect introduction. As Janet said, when neutrinos, by the way, neutrinos most of the time just we said in the beginning they fly through our bodies, etc. They fly through your detector as well. You don't detect most of the neutrinos. But occasionally one crashes into a nucleus, in our case in the ice. We have a detector made of ice. And then it makes blue light. And so we have devices that detect blue light. And as I said in the introduction, to try to do astronomy with neutrinos, it was known since the 70s that you had to build a kilometer cube detector. Well, you cannot buy a kilometer cube of anything. It's too expensive. So you have to go and find it. So the first, find it in a natural place. So the first place people thought of was to build a detector out of ocean water. You go 3 miles deep in the ocean and build a detector. So we did exactly perform that idea, except our idea was we do this in ice. So you go to the South Pole and a mile deep, you fill a kilometer cube of ice.
Well, you have
It's up there behind you.
So we have a display here. So
The Eiffel Tower
If
is for
you-
reference on the right side. That's how big this
so
is.
this is what a kilometer cube. Usually they show pictures of a detector with a person standing behind it, next to it, so that you could judge the scale. Here that's not possible. You wouldn't see a person. So that's the Eiffel Tower. And so what you see here, at the top of that, there's actually a building at the top. The top is the ice shelf. And there you stand about a mile from the South Pole. And so if you then go a mile deep, we took a kilometer of beautiful, transparent Antarctic ice and filled it with 5,000 of these sensors. And so when a neutrino comes in, makes a nuclear reaction, it makes this blue light, it makes a shock wave. We map the shock wave, we know we detected a neutrino, and we can even tell what direction it came from. And that makes it a telescope. If you go outside after the show and you look at the stars, the reason you see a picture of the sky is because the light comes in a straight line at you, so do these neutrinos. But just like you reconstruct the direction with your eye, we reconstruct it with this telescope. So it's very simple. You take a gigaton of ice and put 5,000 photomultipliers in it, which you buy in Japan.
Of course. But you have some drilling animation too to show.
Yeah, there are some minor details I left out. One of them that it took 20 years to do this. And this is how you put sensors in the ice. This is a tool that melts the snow layer at the top, which is about 100 meters thick. And then you have a jet of hot water under pressure that in about 2 days goes 2.5 kilometers deep. It just falls by its weight and melts the ice. And so at this point, you have a hole this big. But it's not really a hole, there is water instead of ice. And so then you sink your sensors into it. And of course, you first take the drill out because you have to use it again. And then once the sensors are in, you let the ice refreeze and you take data. You repeat this 86 times, you have your 5,000 in the ice. We completed this more than a year ago, and so now we are happily taking data.
And what about the data? Are you having more luck than Ray Davis did with the sun experiments?
Well, this detector was built to, what theorists predict we should see. This detector was built that we should see this in over a period of taking data with the full detector for 5 years. If we are lucky, less. If we are unlucky, 10 years. We hope to run this experiment for 20 years. Remember, we are also waiting for a supernova.
Right, there's that.
It has to happen in those 20 years.
But what is your...
Maybe I should turn my cell phone.
What is your holy grail? What is it that you ultimately...
Well, probably a supernova would be the holy grail. The other thing we are looking for dark matter. That's too complicated. There's not enough time to explain this. But kind of what was the sales pitch for building this experiment was to discover the sources of the cosmic rays. As you probably all have read in the newspapers at some point, that's kind of the holy grail to solve one of the oldest problems in astronomy. In fact, it's exactly 100 years ago that cosmic rays were discovered. We have done generations and generations of experiments. We know everything about cosmic rays, except where they come from and how they are accelerated.
We're being bombarded by charged particles. It's sitting here every second. We're being bombarded by charged particles. More if we're in an airplane, less down here, and a lot less if you're underground.
And we have no clue. They are accelerated to energies that make our accelerators on Earth look ridiculous. So you think it must be a dramatic, and it is a dramatic event that's going on somewhere that produces these particles, but we haven't figured out what it is.
It may be exploding stars. It could be something more dramatic.
This would be, this is kind of what, if this detector could deliver that, but I'll settle for a supernova.
And they don't just come from our galaxy. They come from all over the universe. And so they could be coming from hundreds of millions of light years away. The source of them is a very interesting question.
Well, if just that concept, as Francis was describing, is enough to make you want to sign on to the ice cube experiment, keep in mind he has 2 guys who are stuck in Antarctica until February, you were telling me?
Well, since February and at least until October.
Nice.
There are no flights in or out. So In fact, I think we have a picture of the South Pole Station, if we can, yes. So this is
Looks fun.
this is the 6 months that it's light.
Wow.
Now it's dark for 6 months. And on the left, you see the South Pole Station. So we have 2 people there, part of a group of about 40, who are babysitting the experiment at the moment, but the data come back over satellite to Madison, Wisconsin. And in fact, on the right, the line you see is the runway where the planes land. Everything in the South Pole has to go in by plane. And the IceCube project is what you see on the right-hand side of the picture.
Wow.
And one of the amazing things that amazed me, because there are lots of scientific experiments at the South Pole, when I first learned it, is what Francis just said, is that there are no flights in. I mean, we go to space, we go to deep ocean, but the South Pole closes the beginning of winter and opens up again at the end of winter, and you're stuck there.
Nobody knows how to safely, to build a plane that can safely fly at minus 100-degree temperature. It doesn't matter what the units is, are centigrade or Fahrenheit.
Well, while your team is in long underwear down there shivering, you are in a toasty lab somewhere.
That's right, with lots of people, it's great.
With making man-made neutrinos.
Right. Although the methods that we use to produce our neutrinos are not very different from the method that the cosmic rays use to produce neutrinos that we see on Earth. So it's exactly the same idea. We have to accelerate up protons, and then they run into stuff, beryllium usually, and what comes out are particles that decay into neutrinos. And so we're picking up on what nature did in order to produce these neutrinos, but we would really like to know how nature really accelerates to very, very high energies. That would be wonderful.
Yours is called Mini Boon?
Yeah, my experiment is named Mini Boon.
Mini? What does that mean?
Small, mini, booster neutrino experiment.
Okay.
There's a band named after us.
Really?
Yeah, that's how you know you've really made it, when a rock band is named after you. And they seem to really like us. They review our articles on their website. I'm not kidding.
We got to introduce them to our rapper.
If you go out and Google Mini Boon, you used to get my experiment first and then them, and now they're ahead of us.
We have that problem with IceCube.
Yeah, right.
But I was going to say, Francis, you should really, you would think that Francis would build this in the Mediterranean, right? You could go down in the ocean where it's warm, you can be on the beach and so forth.
The first version was near Hawaii.
Right. The problem is that his problem there is the luminescent shrimp, right?
Yeah.
Yeah.
The ocean is a much harsher environment.
Actually, but I think we beat IceCube. You should go and check Google tonight. Yeah, I think we do.
Well, the more hits you get, the more you're going to...
But as a theorist, of course, and watching different types of experiments, there's an important difference, and Francis, I'm sure, well, everyone I think will agree, is that if you can create them, you can tweak the knobs.
Right.
And with nature, you can't tweak the knobs.
Right.
And that's the difference.
Yeah.
So with a particle that you can't see, how can you be sure that the interactions that are happening are actually due to this particle? Well, I can turn my neutrinos on and off. And I can look and I can make sure that the interactions that I'm associating with my calling the neutrino interactions are actually associated with the beam and when the beam is really there. So there's a real advantage to that. And also, I can make different kinds of beams. I can decide I would like to have an electron neutrino beam, or I would like to have a muon neutrino beam. And I can make all of these using accelerators of different kinds. And so I actually find it, and also, you can use the cases where neutrinos are being made for you, for example, at reactors. That's a really nice example of where you can take your detector and snuggle it up next to neutrinos that are coming out for free.
And I think that it's interesting to see what's happened for neutrino physics. And in fact, in a lot of science, often discoveries are made from astronomy lately. We discovered neutrino masses really from astronomy. And we discovered dark energy from astronomy. But once you make the discovery, in order to investigate the particle physics, then you build devices that allow you to tweak the knobs. But you don't know what kind of devices to build until the discovery is made. And for example, if Francis experiment discovers some interesting new physics associated with cosmic rays, it'll direct experimentalists on Earth to maybe build the right kind of detectors. But without that guidance, you can't do it. So there's great discovery potential because the universe produces accelerators like we'll never be able to produce on Earth. No, independent of the gross national product of the United States or whether we have a sane government, we won't have the money to build a detector that produces the kind of energies, or an accelerator that produces the kind of energies that they're looking for in IceCube. And so you've got this universe which provides you with amazing discovery potential, and then you have ingenious experimenters on Earth who try and tweak the knobs and build things to detect them.
But this emphasizes why I think neutrino physics is so much fun to work in, because to be able to do neutrino physics, you do have to know something about astrophysics. You have to know something about particle physics. It turns out you also have to know something about nuclear physics in order to be able to work with these things. So it's a very, very rich environment. A lot of space to explore.
We should actually mention that we discussed how the neutrino was discovered by putting a detector close to, in fact, it was the Savannah River reactor. Neutrino physics is still done very successfully by the same method, building detectors that you put close to reactors.
Yeah, I have a detector
and of course now the
reactor.
big reactors are in China and Korea.
And France.
And France, and that's where the experiments are done.
In fact, I alluded, and maybe it's worth mentioning, one of the reasons that neutrinos are interesting is they may tell us why the universe is made of matter, not antimatter. In order for that to be the case, there has to be an asymmetry between matter and antimatter at some level, and it's related to something called CP violation. Doesn't really matter. But if that comes from the neutrino sector, there are certain properties of the three neutrinos. And one of the most interesting experiments at the forefront of neutrino physics is looking to try and understand the masses and relationships between the neutrinos of all three different types. Because if that relationship isn't there correctly, then neutrinos can't be responsible in some sense for the matter-antimatter asymmetry in the universe. And that's happening at a reactor in China right now.
Basically, what he's saying is that, I said that neutrinos had a kind of clock that they tick. They go from electron to muon to electron to muon. And if the neutrino ticks differently, electron to muon type neutrino from an antineutrino, if their clocks are different, you can end up with this effect where you end up with more matter or more antimatter being produced in the universe. And
antimatter sounds really strange, but it's not. It's the same as matter. The law of the physics tell us on the whole, it's very similar. It's not.
But they should cancel each other out. But we're here,
so it's lucky that you don't know anything about antimatter.
If Francis weren't here, I'd say that neutrinos, antimatter is strange in the sense that Belgians are strange. But Francis is Belgian. But no, forget Francis for the moment. I could ask the audience, how many Belgians are there? You see, they're not strange. You just never see them, and that's just it. It happens. We live in a universe of matter, and it could have been a universe of antimatter. It would look very similar, but there has to be this slight asymmetry, and neutrinos may give us the key to that.
So in fact, that's an experiment that I am starting to do work on to see if we can actually develop a new kind of accelerator in order to be able to look for this clock ticking at different rates. And I think that that's a really nice aspect of what we work on, because if we can produce this new kind of accelerator, it'll have all kinds of commercial value too.
Right.
And so, by doing this work at the same time, we're actually producing something that can be really quite useful.
I was reading about an application for communication using neutrinos to send Morse code, essentially, through any substance.
Right. So actually, it was the Minos experiment demonstrated this recently. They actually sent a message to Minnesota, to a detector in Minnesota.
And the message was neutrino, right?
Something like that. That's right.
But that's another reason, by the way, why a lot of money has been spent on neutrino physics. I was involved once. For the Defense Department spends a lot of money on neutrinos, and you know why? Because submarine reactors produce neutrinos, and one of the things that makes nuclear submarines safe is you can't detect them, and so in the event of a protracted nuclear war, they're kind of safe. But if you could detect neutrinos from those reactors, then we'd know where the submarines are, and that's one of the reasons for better or worse, that the Defense Department has spent a long time trying to think of neutrino detection schemes to look for those reactors that power nuclear submarines.
Well, as you pointed out, Geordi in Star Trek, those glasses, those are to see neutrinos, right?
And there, I'm
I really
contractually
need some of
obliged to
those.
mention Star Trek every time I appear somewhere. But yeah, Geordi's visors detect neutrinos. There's also, in my mind, one of the neatest things from Star Trek that's relevant to neutrinos is there was an episode of Deep Space Nine where I have to tell you, because it really points out how truth is stranger than fiction, it seems to me. So there's this guy, his name is Quark, he's a Ferengi, which is, if you don't know what that is, that's a civilization that, unlike our own, values money. And he gets a hold of he has a gaming casino, and he gets a hold of a device that'll change the laws of probability. And of course, he makes money. And the science officer detects it by sending a neutrino beam through the facility. And she finds that the neutrinos are coming out left-handed, which sounds stupid. But it's not stupid, because that's the nomenclature that scientists use, because elementary particles, many of them are spinning, and if they're moving this way and spinning that way, they're left-handed, spinning that way, they're right-handed. And she discovered that they were only spinning one way. But the amazing thing is, the neutrinos we see are only left-handed. And so I like to think of the story writers from Star Trek trying to come up and think of the stupidest thing they can come up with, and it's true.
Yeah.
Well, there's, of course, you touched on sane government and funding and those sorts of things, but as CERN dominates particle physics in terms of a research accelerator, could neutrino science be the future for us, the saving project for American efforts in particle physics?
Well, it's certainly true that we would really like to develop a new laboratory for neutrino physics here in the United States. And we're talking about building this at the Homestake mine, which is actually the same place where Davis did his original experiment.
That's in Minnesota, right?
No, that one is actually in South Dakota.
Oh, okay.
And so we already have some neutrino detectors around, and we do have one in Minnesota, which is why you were asking about that. But this is a beautiful mine in the sense that it has a lot of infrastructure already there. It has a lot of space that's already mined out where we could actually put our detectors, and they're no longer using it as a gold mine.
It's actually, there are actually particle physics experiments looking for dark matter that are being built down there, and we'd hope that we could build a big neutrino facility as well.
Right, and so then, very much like the kinds of experiments that we have been doing where we shoot a beam from Chicago area to Minnesota, we would actually like to shoot a beam from the Chicago area to this mine in South Dakota. That's a longer distance. It gives us an opportunity to look for a different oscillation than what we were looking at. I think it could be really very important and beautiful experiment, and something that can really be at the forefront.
And it may be one of the, as you pointed out, for better or worse, maybe one of the few places the United States may still be doing fundamental particle physics at an accelerator-based facility. We, with the wisdom of Congress, canceled a machine which would have been more powerful than the Large Hadron Collider and would have come online 20 years ago. And it is unfortunate.
That was the one in Texas?
The one in Texas. Yeah. And now the forefront of accelerators right now is in Europe and in many areas. In fundamental physics, the United States is just doesn't have the facilities.
We brushed past it before, but we talked about it being in the news, the research in Italy, where they came out and said they found neutrinos traveling faster than the speed of light, right? School us on exactly what they found and where that stands
What
now.
happened was that the CERN experiment produces neutrinos, and just like Janet was saying, here in the United States, we're going to produce them one place and detect them in another. In Europe, they were producing them at CERN, and they were going to detect them in a tunnel, actually an automobile tunnel in Italy. And what the claim was that when they detected these neutrinos, they thought they knew the distance pretty well with GPS. The neutrinos were arriving 60 nanoseconds too early, and that suggested they were going faster than light. We all knew it was wrong. I knew it was wrong for one obvious reason, that nothing arrives early in Italy, if you've ever been there. But in fact, the trouble was that physics is not a set of little empires. The speed of light as an absolute speed limit is not just a dictum that's used somewhere. It's an integral part of all the rest of our ideas. And for that to be the case for neutrinos and not violate something else was so astounding that most theorists realized was wrong. And indeed, we now understand there's an experimental flaw that caused it.
Also, one of the very important aspects of this goes back to the supernova 1987A, because those neutrinos came from a very, very long distance, and they would have arrived 4 years earlier than the light if they had been going the speed that was being suggested here. And we know that's not true. We know that we saw them in time with the light, or within about 3 hours.
But,
Although I do think that someone went back and looked at the data to see if there was a peak 4 years
Big
earlier,
peak
too.
earlier.
Yeah.
But
it's
there
hard
is an
to-
important lesson here because, you know, you were convinced, everybody was convinced this couldn't be true. We discussed actually how nobody can conceive anymore that the laws of energy conservation are violated. But when you face an experimental result, it doesn't matter what you believe.
Yeah.
So they presented this. They had this result actually for about 2 years, and they couldn't make it go away. So they presented, this is science. I mean, everybody went after finding ways to prove this wrong or to check it, or fortunately, or they corrected the result themselves a few months later.
But there were other experiments being set up because it obviously was such a... It's right, until we could discover why it was wrong, although many of us suspected it was wrong, you take nature at its face value, and the way to really check an experiment is to confirm it with another independent experiment. And so there were many proposals in the United States here to try and to do an experiment with similar sensitivity, with the type of experiment that Janet was talking about, producing them in one place and detecting them in another. Happily, not happily for the people who run that experiment, who had to resign later.
they did.
Yeah, they did, and that's
been
an
designed.
internal issue that the experimenter has to deal with. But happily for the rest of the community, at least, they discovered their own problem.
But it will create undoubtedly a string of future experiments to check the speed of light of neutrinos. Now that the idea is out, you know, this is a sure Nobel Prize. I can do this.
Right.
And you never know. You
Yeah. In
just
fact,
check
we've
it
already
and
all invested
see what
in the
happens.
equipment.
Really?
Yeah, as
Yeah.
soon as that result came out, all
Yeah.
of the other experiments went out and invested in the equipment. So we all are now in a very good position to...
Well,
And
maybe
you know
when you
what's
need
another-
more funding, you could just gin up something like that.
but there's another important lesson here. They have the equipment, and if you're an experimentalist, you should do what you can do.
Yeah.
The theory may tell you it's unlikely,
Yeah.
but every time you open a new window on the universe, we're surprised. And so I think the lesson is that the experimentalists, as long as it doesn't cost $1 gazillion, they should do whatever they can do to probe nature, because you never know where the surprise is going to come from.
Well, finally, as we wrap up, just a few minutes left, what else? What if there's something smaller? When you think about particle physics, there's Higgs, the God particle, all of this. What excites you most about what is unknown about neutrinos and what else there is to know about things we haven't even thought of yet?
Well, I can take a
for any-
first shot at it from a very practical point of view. I already mentioned that neutrinos look like the canary in the coal mine for the standard model. And I think, if we create we have actually a pretty vibrant neutrino program in the United States, which includes the ice cube experiment. And I think it may very well be that neutrino physics leads us to the next level, the next level of understanding of the structure of matter. It doesn't have to be the LHC. It could be the LHC, could be neutrinos, it could be both. And I have no doubt that the world eventually somewhere will pursue both. But I think using the neutrinos now as a tool to study the universe at a deeper level, I think that's for me the future of this field. I have no doubt that neutrinos, I cannot see the day that neutrinos will be boring.
I agree with you completely. That's why they're my favorite particles. But I think there's great poetry in science everywhere. But I find great poetry in the neutrinos too, because the presence of neutrino masses, as I said, is suggestive that maybe there's this grand unified theory. Interestingly enough, that one of the predictions that comes from grand unified theories may be that diamonds aren't forever, that matter as we know it is unstable, and even protons will eventually decay. And that would have obviously vast implications for the future of our universe and for our understanding of its origins. But what the poetry I find is that the place where we may see it are detectors that were built because of neutrinos. The big proton decay detectors are built because you couldn't really justify them just for proton decay, but they're so big that you can use them to detect neutrinos. And the super Kamiokande detector that was in the rap song at the beginning detected neutrinos from the Kamiokande detector from the supernova. And so it's the detectors that were built to detect neutrinos that may one day tell us that matter's unstable and the future is even more miserable than we thought.
Actually, we may go full circle on that, because we are, of course, already thinking about studying the instability of the proton using IceCube.
Right.
It doesn't work at the moment, but you could do things to it. So we could go full circle, and the large neutrino detectors could bring us back to this really, truly fundamental problem.
So for me, we've talked about the things that we know about neutrinos in this discussion. There's a great deal going on in neutrino physics that is very peculiar. There are anomalies. There are quite a few anomalies in neutrino physics. I don't try to discuss them here because I don't know which ones will survive as we do tests of these and which ones will go away. I think some fraction will certainly go away. But it's very rich in the surprising things that we're already seeing. And I'm really an experimentalist at heart. I was born an experimentalist in the sense that I don't want to tell nature what to do. I want nature to tell me what it's doing, right? And I think it's telling me through these neutrinos. And so I am really excited about what I think we can learn, even over a very short time in the next few years.
Your passion is infectious. Your knowledge is awe-inspiring. We can't thank you enough. Let me take a picture. I want to tweet this out. We got that. And then let me get all of you. All right, we're going to say neutrino on 3. 1, 2, 3. Neutrino. There we go. I'll tweet that out right now.
Does that mean I can turn my cell phone on?
Yeah, you can turn it on.
The iPhone 5 is going to have a little neutrino.
Very good. You know, you've got the Italians and the Belgians. You insult one more nationality, you get a free water bottle. You want to do that? No.
We have a getaway car.
Yeah. Lawrence, Francis, Janet, thank you all so much. Thank you for being here. Big hand for them. We all hope you have a fantastic rest of the World Science Festival and a great weekend. We'll see you next year, everybody. Thanks for coming.
Neutrinos are some of the strangest and most mysterious objects in the universe. They're invisible.